One of our goals when we're thinking like designers is to be able to have a concept of sizes and shapes. And whatever it is you are designing, you're going to be thinking about sizes and you're going to be thinking about geometry. So what we have, after you go through these slides briefly, there's a short quiz in the course that will step you through these questions, and you can try it as many times as you want. It's not a big deal. I just want you to get some practice here. So in these slides, I want to step through the quiz questions with you and just help you think about it. First of all, here's some kind of zigzaggy block, might be a machine way, or we don't know what it is. And what happens if you know some of the sizes because you've been laying something out, but you don't know the other sizes? What are those sizes? And in the quiz, you'll write those as fractions, and then you'll also write those as dimensions. Depending on what company you work for, you might need to do either way. Then, what if this is some kind of repeating doodad, and you have a whole bunch of them? You have 12 of these blocks, one end next to the other end, 12 of them. How long is that? Well, 12 times 14 1/4, there's our answer. Now, if you're going back and forth between fractions and fractions and decimals, if you have a fraction and you want to convert it to a decimal, that's the easy part if you've got a calculator. For example, to convert the fraction 1/4, you just go 1 divided by 4 equals, and poof, it spits out 0.25 or whatever it is. If you've got a decimal and you want to change it to a fraction, one thing you can do is just use one of these charts. And an awful lot of drafters have these charts sitting right on their desk somewhere. These are handy. And I've put this chart in PDF form in the resources for you, so if you want to grab a copy, go for it. It's also a really efficient thing to begin memorizing some of these, and start with the big ones that are easy, like, you know, a half is 0.5. Maybe the quarters are okay for you. A quarter is 0.25. 3/4 is 0.75. But then over time, see if you can get used to the eighths as decimals and the 16ths as decimals. You'll be glad you did. Now, some calculators actually have a decimal to fraction conversion button. I don't know if yours does. Mine does not. But if yours does, here's how you do it, and that's handy. Texas Instruments are really great. All right, going on to another problem in your quiz. Let's say you have a deal where you're going to want 25 pieces of something, some kind of sheet metal stock, and you want each one of those to be 3 3/32 of an inch long. And let's say, let's pretend that the saw blade you're using doesn't eat up any metal at all. So it's just 3 3/32, 25 of those side by side. The first thing you could do to figure out how long this whole thing is, what I would do, is I would get out my calculator and go 3 divided by 32 and find out what 3/32 is in decimal form. And after a while, you'll get so you know that by memory. And then add that to 3. So 3.093 times 25, how long is that? Now, a little bit trickier. Let's say you've got a piece of sheet metal or flat bar, and it's 25 7/8 of an inch long. and you're going to cut 5 pieces out of it because you're making something or other, and the saw blade chews up 1/16 of an inch of material with each cut, and we call that a kerf. So there's 1/16 of an inch kerf. That's material that's lost. How long can we cut each of those pieces? So this is where I actually put this in the quiz just to illustrate how useful it is to make a sketch for yourself. And you can make a sketch with a pencil on a piece of paper, or you can make a sketch on a CAD drawing. CAD drawing is probably easier. So in CAD, you could actually, if you're at work, you could draw a line that's 25 7/8 long, and then think about, okay, I've got, how many cuts have I got? 1, 2, 3, 4. 4 cuts that are 1/16 of an inch wide. This is why a picture is so useful. Because you might think, oh, I've got 5 pieces, I've got 5 cuts. No, you don't. You have 5 pieces and 4 cuts, 4 kerfs. So 25 7/8 minus 4 times these 1/16 inch kerfs. What does that leave? See if you can wrestle with that. Then there are some questions where you're just converting decimals to fractions and fractions to decimals. Rather mundane. Then, last couple of slides here, there are a couple of drawings of connecting brackets of various sorts where we're given some of the sizes, and we're going to think through what are the other sizes. Now I know you can draw this on CAD and it would be much faster, but I'm hoping that you will think through this mentally to help yourself picture what you've got. So you are going to be looking for each of those 5 sizes that we don't know. You are given the hole-to-hole spacing, the center-to-center spacing. You have a radius at each corner, a radius of 400 thousandths. You have 3 holes, they're 422 thousandths. And one of these angles is 45 degrees. Okay, now thinking about what we know about geometry, this thing here is a triangle, isn't it? And if this angle is 45 degrees, and this angle down here is 90 degrees, how big is this other angle? Ta-da! It's got to be 45. And if this is a 45-degree right triangle, those two 45-degree angles are the same. What else is the same? The sides of the triangles are the same. So we got that going for us. Then, speaking of triangles, do you remember the Pythagorean Theorem? Do you remember what it says? A squared plus b squared equals c squared. Well, we've got a triangle here where one side is a squared, that's 1.300. We've got another side that's b squared, I'll betcha that's the same length. And this distance d from diagonally from one hole to the other hole, that's c squared. So if you've got a squared plus b squared equals c squared, can you figure out how big c squared is, and then take the square root of that thing and find out how big that distance is? If that is bugging you and you want help with that, just let me know. I don't want to freak you out. I just want us to be thinking about these. Okay, and then finally, if we know what that diagonal center distance is, and we know that each corner has a radius of 400 thousandths, we can figure out how wide this overall width is. We've got that center-to-center distance. We've got 400 on one end. We've got 400 on the other end. And this is a trick that comes up in designing a lot, where you think, okay, well, let's look at the B dimension. That's another example. You think, okay, I've got 1 300 thousandths, and I've got a radius of 400 thousandths. Okay, there's my width. No, we have to remember that we've got a radius on one end and a radius on the other end. And that might be obvious to you. It's not obvious to everybody. And I just want to really hammer that home, that that's something we want to keep in mind. Now, this connecting bracket is perhaps more subtle than it looks, trickier than it looks. And I'm thinking about the angles. Let's look at angle J and K, for example. Now, it will help to break this thing down into triangles. And over here on the left, where you've got that 40-degree angle, you've got a right triangle where one of the corners is 40 degrees. What angle does that make the remaining angle that's not 40 and not 90? And if you know what that remaining angle is, you have another one of those, the same size, over on this side. You have two of those together. Together they make up J. Now, I don't know about you, but when I'm facing a situation like this, I actually just go into CAD and I draw a triangle, and then I use the mirror command and I mirror it over there, and then I get my angle dimension command and I measure the angle, just to be double safe, double sure that I know what I'm doing. Okay, and if you know what that angle in there is, and you know that this long thing is 180 degrees because it's a straight line, how big is that one? And again, you might want to draw that triangle in CAD and measure it just to be sure. Okay, what about H down here at the bottom? We've got a radius of 350 thousandths, but it happens on both sides. So if that radius goes all the way around, 350 thousandths on each side of the center line, how wide is that altogether? Speaking of radii, there are two other things, F and G, to fill in. With dimension F, here we have a center-to-center distance, 1.4, and we have a radius of 450 thousandths on each side of each hole. So what's 1 400 thousandths plus 450 on this side and 450 on the other side? Likewise, the height. Now we're looking for dimension G. We've got 1 500 thousandths height, hole center to hole center. Down here at the bottom, a little bit trickier, we've got a radius of 350 thousandths on the bottom. We've got a radius of 450 thousandths on the top. And they're sitting at angles, of course. So 1.5 in height plus 350 plus 450. What does that turn out to be? So there you go. Hope you're not mad at me for giving you these stupid problems, but I think it's good to grind the rust out of our brain cells and start thinking about sizes and shapes. And now next time, we're going to start thinking about our dimensioning rules.